So the model I would like to consider first is the local trend model. And in order to understand the basic stochastic volatility model, let's start here. So we have YT, our return process, which we observe on the market. It has some error term, additive this time, ET, and it is fluctuating around some mean mu. Okay, fair enough. This mu we do not observe. This mu follows its own life and has its own error term eta t. So think about epsilon t as a return process. You have your zt, a normal random variable, and you have a sigma t component there. Sigma t is a latent process. You do not have any clue how does it look like. And the only thing you know, it kind of has its own evolution and depends on like somehow previous observations of sigma t. Now we go one step further and we say that unlike in the Gartwan-1, it is not ft deterministic. We do say that our latent process, which we for now call mu t, has its own innovation eta t, which is normal. So what I'm describing right now is called in the literature a state space model. We have an equation number 2, which is a state equation or the transition equation. This is how we describe the evolution of the underlying latent process, which we don't know, don't observe whatsoever. We have equation number 1, which is called an observation equation, where we do observe the data yt, and we know it somehow depends on the latent process mu and has its innovation e. If you assume that both of the error terms are normally distributed, that is called a Gaussian state space model. And these particular specifications of the conditional mean of the yt and ut gives you the definition of the local trend model. Okay, so now, what's the problem? The problem is always, of course, you want to filter out the mu-t, recover this latent process. And in order to recover this latent process, the only thing you seem to need is to estimate those two sigmas, right? So sigma squared e and sigma squared eta, once you know them, you can actually kind of recover the evolution of everything. And now I would like to talk about this state space model in a bit more detail and motivate you. Why do we need so much math in the coming lecture? All right, consider a state space model where we have an observation equation and we do observe data yt. So let's say we observe some time series of returns. Now, after estimating an Armagard's likelihood, you are like very easy about that. So piece of cake, right? So you take your ET, which is just the difference between YT and mu-t. And you know that this guy follows a normal distribution with the variance sigma squared e. Well, fine, right? We all remember how a normal density in such case looks like. So you take your 1, then you have your sigma e square root of 2 pi, exponent to the power of minus 1/2, and then you have your ETs divided by sigma e. Yeah, easy. So what do? As a financial econometrician, you write down the log likelihood function, where you would like to estimate your variance of the error term e given the data of yt. Okay, so this you know by heart by now. So you have minus t half log of 2 pi, minus t half and log of the sigmas. And you also have 1 over 2 sigma squared e, and then the sum of all the ETs squared. Okay. So far so good. And you can then insert the definition of the ET. So this looks more or less like a super easy Garch likelihood, right? Minus t half, no time series in the sigmas, so everything is nice. You know how to do that. 1 over 2 sigma squared E, and then the sum of your demeaned return process. Okay, so you do have your data there. And now what we usually do in the likelihood, we kind of plug in what's the mean, the conditional mean specification. So what do we know about mu t? This is mu t minus 1 plus eta t minus 1. So this is the problem, right? So mu t is not some deterministic function which we can recursively compute. However, it has its own innovation, that eta t, which follows a normal distribution with its own variance. So now, kind of here, you need to insert another likelihood for the mu t, which is normally distributed. And that is basically the problem. You cannot estimate the state space model with the normal likelihood, because you cannot filter out two noises simultaneously. You have two error terms. So here, instead of mu t, you would need to insert the random variable, which you cannot do. Your likelihood then becomes a random function. So you do not know how to optimize random functions, and this is very sad. So that is why we're going to learn something different, an alternative estimation method, which helps us to estimate the state space models. Okay, so we have just seen why cannot we estimate this model via the normal likelihood. Okay, we have this mu t, which basically has its own innovation, and therefore we cannot insert it in the log likelihood function, because then the log likelihood function becomes, normally distributed. Very difficult. So the goal of our new estimation method is essentially to recover this latent process evolution. And once you have done that, you can say something about your observation equation and yt. We have a state space model which you could simulate, and important to distinguish are the cases with different signal to noise ratio. So you have your kind of mu t evolution, which has the sigma squared eta variance, and you have the evolution of the noise component et. And mu t is referred to as signal, the latent process, and et is the noise. So if your eta t is much larger than the sigma squared e, then your y and mu, they're more or less coinciding. If the ratio is 1, then you have y in the blue line, red corresponds to the underlying latent process mu. So okay, there are some errors, but you do have like big trouble when you have very low signal to noise ratio. So your underlying process mu is somehow this red, more or less stable line, and then you have the y process, which is this blue line, which is distorted by the noise sigma squared e. And this is what you see, of course, in the financial data, right? Life is not easy, so we are usually working with a very shitty data in that signal to noise ratio sense. The state space modeling actually came from the brain signal processing. So what we're trying to do, usually when we look at the human beings, we're trying to understand what kind of part of brain is responsible for what, and then you can, of course, measure the y, the blue line, the signal, the electrical signal of the brain, but it is distorted by some noise, and your job as a scientist to recover the red line evolution. And in physics and in biology, you usually have some like good signal to noise ratio where you can recover the underlying process mu relatively easy. In finance, of course, I mean, this is what we have, lots of noise, very little signal. So what we're going to learn is called a Kalman filter. A Kalman filter is an estimation method which is used for state space models. We will first consider Kalman filter for the local linear trend model, and only after we understand how that works, we will move next lecture to the stochastic volatility model estimation. So, we want to do three things. First, we want to recover our latent process mu-t. That is, we want to remove measurement error. Then we want to estimate the mu-t given all the information available to us up to t, and then we want to forecast. We want to forecast the latent variable, we want to forecast volatility. So Kalman filter is basically just an algorithm which does these three things. And I'm going to look at the Kalman filter derivation, which comes from the properties of multivariate normal. But of course, you could look at the other proofs. The original proof of Kalman is based on orthogonal projections, and depending on your math background, you also might find the other density specifications useful. So Kalman filter I'm talking about now is the baby simple version. Okay, there are extensions. So now let's try to understand the estimation method for the local linear trend model, which is a state space model, using the Kalman filter. Before we do that, we need to remind ourselves what is the multivariate bivariate normal distribution, and now we need to remember certain properties of that. Okay, so take a deep breath, and here we go. We have two variables, x and y. They're jointly normally distributed. And here I will write down the notation in a very general form. So I will write mu x and mu y. That is going to be the vector of the means. And then I have the variance covariance matrix, where I will allow the variance of x and covariance between x and y to be matrices as well. So you can think of those as like vectors themselves. So you have two random vectors, x and y. Each and every one of them has some variance matrix and some covariance between each other, and they're jointly normally distributed. And now what I would like to derive, I would like to derive the distribution of x given y. So how are we going to do that? We consider first a linear transformation of x, which is called z. We will say that, okay, we take our random vector x and we take our covariance between x and y, the variance of y inverse, and the mean y. Okay, so in the scalar world, that would be x minus sigma squared y divided by the covariance between x and y minus mu y. Okay, but I'm not doing scalars, I'm here doing the more general case, which we will find useful later on. Okay, here we go. Expected value of this linear transformation of x variable equals to expected value of x minus those covariances and variances. They're just matrices from the data generating process. They're constant. They do not have any distribution. What has a distribution is a random variable y and x. And if you look at the second term carefully, you will see that once you put it out as the expected value of y minus mu y, it will become 0. So the whole thing would be just denoting the expected value of x, which we denote as mu x. Next step. The second thing we need to learn about the z, it's more or less its squared form, so kind of ingredient for the variance. So here we go. We need to plug in the definition. x minus sigma xy, sigma yy inverse, y minus mu y, and then multiplied by the same thing transposed. We then open the brackets. When you transpose this term, you want to remind yourselves that you need to reverse the matrix multiplication. So it will be y minus mu y prime, sigma yy inverse, sigma xy prime. And then the second term, this is minus, and the monster term. Okay, so now let's go step by step. The first term kind of remains the same. Then we open the brackets in the second term, this one. So we write down the expected value of x and y. Remember, they're jointly distributed, so we cannot just write it down as the expected value of x times the expected value of y, because there is a covariance between those guys. Note that mu y and the sigmas, they're just parameters, right? So they do not have any random variation. Then we do the same with the second term. And then if you look at the monster term, then you immediately notice that the y minus mu y and the same thing transpose would denote nothing else, an expectation especially, as the sigma yy, which can cancel out with some neighboring sigma matrix. All right. Then we can simplify this expression a little bit more. So what do we have? X prime. And then we can combine the terms which have the sigma yy inverse sigma xy prime on the left-hand side, which will lead us to the following. You have the mu x mu y prime minus expected value of xy prime, and then you have the yy inverse and the covariance transposed. Then you do the same for the terms which have the covariance times the inverse of the y variance in front. That would give you the ymx prime minus expected value of yx prime. And finally, the last term, which is the covariance, then only one inverse of the variance of y, and the covariance transpose. The next thing you would like to remember is that if you like to write down the expected value of x and y in general, you can use the covariance expression for that. So by definition, covariance is just the expected value of the product minus the product of expectations. Thus, you can express the mu x and mu y essentially minus the expected value of the product as the minus covariance between x and y. And this property also holds in matrix world. Thus, we can continue our derivation and simplify the second and the third terms. Okay, so we have instead of the first bracket the covariance between x and y. So this is mu x mu y minus the product of the expectations, y inverse x y prime. And in the second term we have the same expression but transposed. So that would be the minus the covariance, but it is transposed. And then you immediately see that terms cancel out, and we are left only with expected value of x prime minus the covariance times the inverse of the variance of the y and the covariance transposed. So that was the expected value of z prime, by the way. So that's the guy. Okay. Now, next thing we need to learn about the covariances, about the z transformation. So we need to consider the variance of z. Okay, so by definition, it is the expected value of the square minus the square of the expectations. So now we can combine our knowledge and write down the expected value of x prime minus the term we have just derived. And we also remember that the expected value of z is nothing else as the expected value of mu, so we have mu x prime. Now, as you can see, we have the definition of the variance of the x variable. So that is denoted as sigma xx minus xy, y inverse, and the covariance prime. Another useful property of the z transformation is this covariance between z and y. By definition, if we consider that, it will be y minus mu y and then z minus mu z transposed. That would be the covariance matrix between z and y. Right, then we write down the definition of our z. Okay, what was z? X, and then some kind of part which depends on y. This was the mu x, and then the part which is depending on y. Okay. So we open up the brackets to see that I forgot the transposed, y minus mu y, and then you have x minus mu x transposed as one term, and the second term will be the expected value of y minus mu y, and then you have, because you have the transposed product, the y minus mu y transposed, the sigma y inverse, sigma xy. What stands as a first term is the covariance matrix, but it is transposed, right? Note the change in the ordering of the multiplication. And then we have the sigma y here. Then we multiply it with the inverse. And thus you are just going to have the sigma xy prime, which is 0. What does it tell you? Well, it tells you that you have your variable z, which is some linear transformation of x, and y and z are uncorrelated. So this is crucial. So now instead of doing the distribution of x and y, we can do the distribution of z and y, because what? We know that they have nothing to do with each other, which is convenient. So what have we just seen? We have seen that if you consider the z variable, it will be normally distributed, as it will be distributed as x with the mu, and then we have derived the expression for the variance of z. And we now remember that x can be expressed as the z plus the term which is kind of depending on the y. We know that those two parts are uncorrelated, and therefore we have arrived to a very important result, that is, we can characterize the distribution of x given y. which will be normal with the mean, mu x plus the term, and the variance will remain the same. So for given y, this adding those constants does not have any effect on the variance of the distribution of x given y. So for fixed value of y, the variance of x will be the same as the variance of z. And that's basically the key result which you need in order to understand Kalman filter. All right, so what have you just derived? We have seen that if we have two random variables which are jointly normally distributed, there is some covariances between them and so on, then we can characterize the distribution of random variable x given variable y values. And we know the mean of the distribution and variance. Okay, so you have explicitly written down the expected value of x given y, which we are going to use in the Kalman filter derivation, and the variance of x given y. You could do kind of an extension of this result and do like three guys, x given y and z, x given y and z, and you can express the, if you have three guys distributed all together, you can insert the term for the third variable. So you can practice your linear algebra knowledge by deriving that. For our purposes, we will use only, I think, the bivariate case. Okay, so where were we before all of that? We were trying to understand what is the Kalman filter, where we have a state space model. We have an observation y, we observe this data, we know it's a function of the latent process mu, and some error term e. And then we have a latent process evolution, which troublesomely has the eta t, the error term on its own, has its own life, a random error. And it's very inconvenient because we cannot do likelihood. Instead, we are going to do Kalman filter. In the Kalman filter, what is our purpose of this Kalman filter? We want to filter out the evolution of the underlying state equation. So we want to filter out the mu's. Once we know the mu's, we can forecast them, and this ultimately determines the evolution of the observed return component. If we want to forecast the underlying volatility process, we first need to recover it from the data we have. Again, this sounds very complicated, but now we will see in a minute how can we derive the filter of this. So this is kind of an algorithm or a process. How are you going to recover the mu process, the latent process, from the observation equation? So now take a deep breath and let's begin the derivation. So Kalman filter is named after a guy called Kalman. He was, by the way, riding BMWs all the time. And now we need to concentrate on a simple model, which is local linear trend model. You have your mu-t evolution, which you can write down, for example, as mu-t given mu-t minus 1 plus eta t minus 1, if that's more convenient notation for you. Important to note is that we have two independent noise components. So the e variable is e, this is the variable called eta. Right, Kalman filter basically needs some preparation. Something we need to understand about this model before starting to write down how can you recover the latent process out of it. So we first define something which is called a forecast error. A forecast error is denoted by nu-t, so in LaTeX that would be nu, and this nu-t is the difference between your data point at time t minus the expected value of yt given past filtration. So at time period t, you are doing a forecast, which you can then evaluate. So your forecast error. At ft minus 1, you did a forecast for yt, and then you compare your actual data realization with your forecast, and that's going to give you the forecast error. And now we're going to introduce a very compact and convenient notation that is, instead of writing down all the time these conditional expectations, we're going to denote them as t given t minus 1. So this is what you expect of yt if you have only information up to period t minus 1. What is your actual forecast? So if you are given the state space model above, how are you going to forecast your yt when you have information only available up to t minus 1? Well, you're going to use the observation equation. So it's going to be mu t plus et given ft minus 1. So essentially, in order to forecast your yt, you need to forecast the mu t given the ft minus 1. And here's the trouble. You actually have no clue what is mu t. You don't observe it. However, we will denote this guy by mu t, t minus 1. That will denote always the conditional expectation. Next thing, forecast error variance. Forecast error variance will be denoted as capital V at point t, would be denoting actually the conditional variance, to be precise. So we are talking about the variance of our forecast error term mu t with the past filtration. So at period t minus 1, what can we say about our forecast error variance? We plug in the definition of the forecast error variance, which is yt minus the forecast, which we have just seen is the conditional expectation of the latent process mu t. And here we are already seeing some simplification. Before simplifying that part, we can write down the expression yt more implicitly. Mu t plus the orthogonal noise et minus the conditional expectation of mu t. Note that at period t minus 1, the only thing you expect from the orthogonal noise is for this to be orthogonal. So the et has nothing to do with mu's, it's generated independently of that. Therefore, we can ignore all the covariance terms when we're writing down the variance of the sum of two random variables, and we can just write down the expression for mu t minus its conditional expectation at t minus 1 given past filtration, and then the variance of et given ft minus 1. Again, et is orthogonal to everything, so no covariances. Here's a new bit of notation for you. We are going to denote those guys as the sigma t given t minus 1, and this is sigma squared e, okay? So what is this new notation, sigma t given t minus 1? That denotes the variance of the mu t given ft minus 1. If you consider this term, you are going to see that given ft minus 1, this is a constant. So the variance of mu t minus its conditional expectation given ft is the same as just the variance of the mu t process, the latent process, given information ft minus 1. A couple of final bits. We are nearly set up to actually write down the Kalman filter, but before we need to look at our forecast error variance properties. So we apply the law of iterated expectations in order to derive the conditional variance, the unconditional mean, for our forecast error term. So we have the ft minus 1 expectations, and we have just seen that basically it is going to be expected value, and then instead of forecast error, we're going to insert yt minus its conditional expectation, ft minus 1. That is going to be the expected value of yt given ft minus 1 minus the very same thing, which is 0. So our forecast error has a mean 0. Second thing, let's consider the covariance of our new t, our forecast error, and some y, the data at some time j. Because of the 0 mean of our forecast error, that would be nothing else as just the expected value of the product. And then again, we can apply the law of iterated expectations. So we condition everything on ft minus 1 because the forecast error variance is the conditional forecast error, conditional on ft minus 1, so it's always useful to condition everything on ft minus 1. And then I can just put the yj out of the expected value operator to have our conditional moment of the forecast error variance new, and then for all j's which are smaller than t, I can do that to prove basically that this whole thing is 0. Thus, my forecast error variance, the conditional forecast error, not variance, my one step ahead conditional forecast error has nothing to do with the previous observations of the data. Okay, so why was I doing all of that? Stay with me. So now the whole magic becomes when I'm considering the joint distribution of mu t, the latent process, and the forecast error nu t, given ft minus 1. So conditional on ft minus 1, they would be jointly normally distributed. So what we have just derived? We have derived that we denote conditional expectation of mu t given ft minus 1 as mu t, t minus 1. The conditional expectation of our forecast error is 0. Yeah, so given ft minus 1, we have shown that this is 0. So this will be our vector of means. And then, what is the variance of our mu t given ft minus 1? We denote it as sigma t, t minus 1. What is the variance of our forecast error? We have denoted as vt, but it's nothing else as just the sigma t, t minus 1 plus sigma squared e. Okay, so now I will derive the covariances. So what is the covariance between the latent process mu t and the forecast error nu t given ft minus 1? Well, you can write down, because we know that the conditional expectation of nu t is 0, so that will be again just the mu t times nu t given ft minus 1. Then we plug in the definition of the forecast error. So we have our mu t minus yt minus mu t given t minus 1. All of that given past filtration. Now, instead of yt, I again write it down in terms of just the mu t plus et, the orthogonal noise, minus conditional expectation. Okay, and then we can isolate the orthogonal noise and write down that we have the expected value of mu t, and then we have mu t minus its conditional expectation. and another term which is about the expected value of mu t and the noise. Okay, so now this of course is 0. We now need to pay a little bit attention to the first term. So recall that when we were defining the sigma t minus 1 notation, we have said that, okay, that will be the variance of mu t, our latent process, given ft minus 1 past filtration. Now, by definition of the variance, we can write it down as the expected value of the mu t minus its conditional mean squared given ft minus 1. Right, then we open the brackets. So we are going to have mu t squared minus 2 times mu t t minus 1, and the conditional expectation squared. I can write this term down as minus mu t minus 1, and another one, right? Then I'm going to combine the first two and the second two terms and write down the first term as mu t and mu t minus the conditional mean. And the other terms I will pull out of the expectations. So we will have mu t, this will be with a minus, ut given t minus 1 times the expected value of the mu t given ft minus 1. And again, I'm using just the fact that given past filtration ft minus 1, I have this term kind of constant. It's not a random variable anymore. Okay, so this term denotes mu t minus 1, and these two last terms, they cancel out. So what is sigma t minus 1? It's nothing else as the term which we see here. What we have just shown that the covariance between mu t and the error bt would be sigma t minus 1. And that completes us with the sigma t minus 1 and sigma t minus 1. So given that result, what can I recover using the properties of the normal distribution? I can recover the distribution of mu t conditional on the mu t and ft minus 1. Using just the properties we have been looking at when we looked at the normal variables x and y. What we have derived before is that if we have a joint normal distribution, we can get the x given y as the normal with the mean ux plus sigma xy, sigma yy inverse. Then we have y minus mu y. And then we also have the explicit expression for the variance. So with this result, as I have mentioned before, I can characterize the distribution of mu t given ft minus 1 and the forecast error term at period t. This is very important to understand. Please do remember our state and space equations. So we have our mu t plus 1, which was mu t plus the eta t. What is important to understand? The nu t, our forecast error, can be written down as yt minus the conditional expectation of mu at period t minus 1. So the information set of y and the forecast error is kind of the same. Now, note also that the only kind of information I receive at ft, of course I have the ft-1 information contained in ft, but the only kind of new guy which comes in as an information set would be yt. Once you know yt and ft-1, it's the same as writing ft and the new t. Very important that what follows immediately from staring at those equations is that if you would like to recover the expected value of your latent process mu t given time t, given you have the new information on yt, it is essentially the same as writing down the expected value of your mu t given post filtration t minus 1 and yt. Or it's the same as writing the expected value of mu t given the post filtration t minus 1 and the forecast error mu t. Because I have this fantastic result on the distribution of mu t given the forecast error at time t and ft minus 1, this is the same as saying that I can characterize the distribution, the whole distribution of my latent process given ft information set. And this is crucial to understand. Please take a break right now, pause this video, stare at these equations and internalize the thought. Okay, so now, what am I going to do? I'm going to actually write down the expected value of my latent process t if I have my data at time period t. So I do observe yt already. By the properties of the normal distribution, I'm just going to write down this expression. So mu x, this is mu t minus 1. The next guy, sigma xy, this is epsilon t minus 1, right? The covariances. Next, sigma yy inverse, that is vt inverse. And then you have y minus mu y, so the forecast error, minus its mean. Okay, and then we write down the whole term as mu t given t minus 1 minus, plus epsilon t, sigma t minus 1 nu t divided by vt. And what is common notation in the literature is to use the capital KT to denote Kalman gain. Kalman gain is the ratio of the variance of your latent process to the variation in the forecast error. So that is called Kalman gain. Okay. Finally, you can write down the variance of mu t at time period t using the very same result from the multivariate normal. So you will have sigma xx minus the covariances squared divided by the variance of y, and you can write it down as sigma t minus 1 minus the Kalman gain. Okay, last steps. I promise we're nearly done. You need to write down the Kalman filter gain, Kalman filter steps for prediction. In order to predict your evolution of latent process, expected value of mu t plus 1 given time period t, you need to write down the equation where you see the evolution of mu t. So you have to write it down as mu t given ft, because the orthogonal noise eta t has nothing to do with mu t. Thus, what you have just learned is that your prediction for the t+1 evolution is just a mu t, standard unit root kind of story. Finally, the variance of this guy can be also predicted, and we can write it down as the variance of mu t plus 1 given ft. That would be the sigma t given t plus the variance of the error term. So the variance of this guy, conditional on ft, plus the variance of the random component. Now, your job is to write down those equations in a nice form somewhere you can look them up. Because essentially, we have just derived the Kalman filter. So now, what is happening in real world? In real world, you have your y1, yt. Then you need to initialize your filter. That is, you simulate your mu1 from a normal distribution with some starting values for mu t0 and sigma 1, 0. Okay, once you initialize your filter with two values, which you usually kind of take from the unconditional distributions, your forecast error at time 1 would be your data, which you have, your return number 1, minus the value you initialize your filter with. Okay? Then you can compute the forecast error variance, which by the formulas we have just seen would be just the sigma tt minus 1. This is your initial value, plus the sigma squared of e, which you need to estimate immediately. You can write down the function for Kalman gain, which will be just the sigma divided by this variance. Note that they are all now functions of those sigma squared parameters. And then you write down your predictions, which is the mu t minus 1, the initial value, plus the forecast error at time 1, times the Kalman gain. And you can write down the sigma expected value for sigma period 2 given ft, and then you write it down in terms of your initial state minus 1 minus Kalman gain plus the sigma squared eta. Okay, and then you iteratively repeat the process. What have we just seen? We have seen the derivation of the Kalman filter for the local linear trend model. The first step of the Kalman filter derivation is to define the one step ahead forecast error in terms of the information up to t minus 1. Then you express it in terms of the conditional expectation for the latent process. You then note that the forecast error is kind of independent of the past filtration, and what it brings you is the new information at t, right? You can show this and express the conditional variance of the error term given the past filtration as the new notation sigma tt minus 1, which just denotes the variance of the mu's, and the sigma squared of the e. Then you look at the properties of your forecast error, see that it does not depend on any past information yj, and then you characterize the joint distribution of mu t, the latent process, with the forecast error mu t given ft minus 1, and then using the normal distribution you're able to derive the conditional expectation of mu t given mu t and ft minus 1, which just constitutes the ft information set, which you then can write down in terms of your forecast error variance and the Kalman gain. Similarly, you do with the variance. And what is the Kalman gain? It's basically the contribution of the new shock, mu t, to the state variable mu. So how much kind of variation relatively do you bring compared to VT? What was VT? Once again, the VT was the forecast error variance. Sigma t is the variance of the state variable mu, and then the ratio of those would be, so how much does the new shock contribute to the variance. And then using this Kalman gain ratio, you could easily write down the expressions for the expected value for your state variable given ft and the expected value of its variance given ft. Note, you do not observe it. The only thing you can operate with are those expectations. Then you can forecast them. We have a unit root process, so the forecast for the state would be the current expected value. And you can do the same forecasting the variance of your state variable. So here you go. You have just learned the Kalman filter for the local trend model. If you have a state space equation in where you have two unit root processes, you can estimate the variances of sigma squared E and sigma squared eta by initializing your filter and then recursively writing down the forecast error, its variance, the Kalman gain, and then the predictions. Then you do this recursively for each and every observation yt you have in your sample. And then you can write down the maximum likelihood, right? The log likelihood function for the Kalman filter, where you can use those recursive iterations to recover the sigma squared E and the sigma squared eta. Okay, so that was enough for today. Practice Kalman filter derivations for the local trend model. Internalize the information sets difference. Once you are through those derivations, we can proceed to the next lecture, where we are going to talk about how are you going to actually estimate those things with the maximum likelihood.